Hello and welcome to another week of ECE 108. We're going to start out by giving a formal definition of function equality. We've used this before without formally defining it, but we're now going to rectify that and formally define what I mean when I say two functions are equal. Next, we're going to talk about function composition, some properties of function composition, the identity function, and then talk about inverses of the composition of functions. In the next two lectures this week, we're going to introduce the idea of cardinality and talk about some properties of the cardinality of finite sets and infinite sets. So without further ado, let's get into it. So previously in a theorem I said f inverse is equal to f, but I didn't define what I mean by equals. So let's rectify that by formally defining equals for functions. So two functions f and g are equal precisely when the following hold. So I'm going to need three things. One, f and g have the same domain. Two, f and g have the same codomain. And three, for all x in the domain of f, or equivalently the domain of g, f of x is equal to g. So notice here that this third point, along with the first 2 points, implies that the range of f and g are going to be exactly the same. Okay, now let's look at some examples. So if f is the function defined from r to r by this quadratic mapping, and if g is this function defined from r to r by this mapping that takes x and maps it to x times x, then in this case, would the functions be equal or not? I'll pause the video and think about it. Okay, so in this case, f will be equal to g. Why? Well, clearly f and g have the same codomain and domain, and clearly if I take f of x, I get x squared. If I take g of x, I get x times x, and x squared is equal to x times x. Next, if f is the function mapping from the whole real numbers to r0 plus, defined by this quadratic mapping, and g is the mapping from r to r, defined by this quadratic mapping, are the functions equal in this case? Well, no. In this case, while the two functions agree for all values of x in their domain, their codomains are different. Now, to be explicit about my previous comments about claim 20 in the last lecture, in claim 20, lecture 11, slide 12, we need the function to be bijective, otherwise f inverse could have a different codomain than f. So now let's talk about function composition. Are functions of functions well defined? Well, generally when I give you a new object, it's kind of good to try to break it to see if the definitions work and if it's a kind of useful object. For instance, with sets, we can consider sets of sets, but there are some things that we can't consider. For instance, the set of all sets that do not contain themselves. So a natural question to ask is, are functions of functions well defined and can we break them? Well, the answer is that they are sometimes defined, and let's give a definition. If f is a function from x to y, given by this mapping x maps to f of x, and g is a function from y to z, given by this mapping y goes to g of z, then the composition of g and f, what will this be? Well, this will simply be gf, that takes x, the original domain over here, and maps it to z, the original codomain over here. And this will simply be given by the mapping x goes to g of f of x. So I just fixed a small little typo there. So this is a function. So why would this be a function? Well, f takes in a value of x and outputs some element of y. We don't know what it is, but it's something in y. And g can now pick up that f of x and y and map it to something new in z. Thus, since both f and g are functions, this composition will be a function. Okay, so one thing to notice here, order matters. So explicitly, f of g of x is not equal to g of f of x and may not even be defined. I will give a few examples of that in a minute. To better understand what this definition is saying, let's visualize this definition. So visually, I start with two sets x and y. Here, f takes elements in the set x and maps it to the range of f. So this could be all of y, or it could be a subset of y. And now, what does g do? Well, g takes elements of y, including everything in the range of f, and maps it over to z. So now I can build this new function, g of f, that takes all of the x's over here, maps them to the range of f, and then maps them to z. So formally, gf takes things in here, goes through the range of f, that's why I kind of drew the arrow here, and ends up over here in z. So one important thing to note, the composition of GF is only defined when the range of F is a subset of the domain of G. So formally over here in my definition, instead of Y, I can make this any subset of Y, and the composition will still be well defined. So if I ever ask you to prove that a certain composition exists or justify that the composition of two functions exists, your kind of go-to thing to show is that this range of the inner function here is a subset of the domain of the outer function here. So you will be doing that, so just keep that in mind. Okay, let's look at a few examples. If f is a function from the real numbers to the non-negative real numbers defined by this quadratic mapping, and g is a function from the real numbers to the interval -1 to 1 defined by the sinusoidal mapping, let's look at the various compositions we could consider. Is gf defined? So pause the video and think about it for a bit. So here the first thing to note is that f and g are in fact functions. If they weren't, then it wouldn't make sense to even try to talk about compositions. And secondly, we note that the range of f, or the codomain of f, is this R0 plus. It's both the range and the codomain in this case. And the domain of G is R. Is this set here a subset of this set? Well, yes. Therefore, this composition will be well defined. Now, what is GF? Well, GF will be the function that I get when I take this x squared and I plug it in here for x. So in this case, GF will be sine of x squared. Now, secondly, GF, the domain of it will be R, and the codomain will be this interval here from -1 to 1. So GF will be explicitly given by this function here. Now, what about FG? Is this defined? So take a minute and think about it. Well, G, its domain is R. It maps everything to this interval from -1 to 1. This is a subset of the domain of F. Therefore, this would be defined in this case. Further, what is FG? Well, take a minute and try to think of what this one would be. Well, in terms of our domain, the domain will simply be R because that's the domain of G, this inner function here. And the codomain will simply be this R0 plus. So notice here in this case, since I go through the interval from -1 to 1, GF won't have the same range as F. So I get some restriction on my range there, just by the fact that I'm going through a smaller set. So now, what would the function composition be? Well, I'd find the function composition by taking sine of x and plugging it in for x here. So this will simply be sine squared of x. Now, a word of caution, a very common mistake is swapping the orders here. Make sure that you always apply the inner function first and then the outer function. As a side note, there are kind of two conventions used for functions. One where you apply the function on the left first and then the function on the right, and one where you apply the function on the right and then the function on the left. But in this course, we always apply the function on the right first. Don't mix that up. Okay, so now the next question I can ask, does GF equal FG? Well, take a minute and think about this. Okay, so no, these two functions will not be equal. There's two things wrong. Well, the domains agree, so that's good, but the codomains are different. So that's sufficient for the two functions to not be the same function. Further, the functions do different things. Sine of x squared is not equal to sine squared of x. Therefore, no in this case. Now let's look at one more example. Suppose I have a function f from the Cartesian product of r with r into r defined by this mapping here that takes my vector or my ordered pair x1, x2 and maps it to the product x1 times x2. And suppose g is a function from r to r plus 0 defined by this mapping that takes x and maps it to the absolute value of x. Is GF defined? So take a minute and think about this. Well, let's look at it. So the range of f is simply going to be some subset of this codomain R, and the domain of G is going to be R. Therefore, this composition here will be defined. Second, what is GF? Well, I'm starting with a ordered pair x1, x2. I map it to this, and then I want to take its absolute value. So explicitly, this will be the function from r cross r into r plus 0. That will take a ordered pair or a vector of this form and map it to the absolute value of x1 times x2. So here, I explicitly used the term vector, which you have seen before, because you know R cross R is also R2, and it's a vector space from linear algebra. So do feel free to kind of use your intuition from linear algebra when dealing with some functions here. Okay, so is fg defined? So think about this for a second. So in this case, the codomain of G is simply this set here, and this is not going to be a subset of R cross R. Therefore, this is not defined, and to be explicit, it's not defined because the range of G is not a subset of R cross R. So now, does GF equal FG? No, since GF is not defined. So kind of the lesson that we get out of these two examples, GF may not be equal to FG for kind of two reasons. One of the compositions might not be defined, or two, we could have a different range, codomain, or the functions could act differently. So let's make a theorem out of this. Function composition is not commutative. So to be explicit, that is to say fg is not equal to gf for all functions f and g. So note that this is similar to how matrix multiplication is not commutative. So recall, if I try to swap the order of matrix multiplication, there's two things that can go bad. One, it could just simply be the case that the domains and ranges of my two functions don't match. For instance, I can't take a 5 by 5 matrix and multiply it by a 4 by 6. Or it could also be that I get a different result when I compute matrix A times matrix B versus matrix B times matrix A. One more thing to note, matrix multiplication is a type of function composition. Okay, so let's step away from this discussion of matrix multiplication and talk about function composition being associative. So this is to say for all functions f, g, and h, such that the domains and codomains match up nicely, h of g, parentheses around that, of f is equal to h, parentheses, of gf. So you might think this is true because it's true for matrices. But that does not necessarily implies that it works for function composition in general. So we need to give a proof, or in this case, a sketch of a proof. So how could I show that these two functions are equal? Well, I need to show three things. I need to show that the domain and codomain of this function on the left-hand side and the function on the right-hand side are the same, and I need to show that they do the same thing to x. So clearly, h of g is defined. In this case, g maps into y, and h maps from y, so that's well defined. And thus, hg applied to f is going to be defined as well, since f maps into x, and hg maps from x. Thus, this is going to be a well-defined composition. Further, gf is going to be a defined function. Hence, I can now apply h to get that h of g of f is a defined function. Thus, I can say that the domain and codomain of these two functions are the same. Finally, I need to show that these two functions do the same thing for any arbitrary w and w. So to do that, I just simply examine what they do. So for any w and w, h of g, parentheses around that, of f will take an element to w, and it will map it to h of g of f of w. That's pretty straightforward to see why that's true. And h of parentheses gf takes an element to w and maps it to h of g of f of w. Well, these are the same functions, so these two functions are sending x to the same thing. Therefore, I can now say that these two functions are equal for all values of w, and thus the result holds. A good practice would be to formally write up this proof, but let's go on to new topics. So, for functions f mapping from x to y and g mapping from y to z, gf exists, and I'm now going to mention a bunch of things that are true if either f or g are surjections, injections, or bijections. So, if f and g are both injective, then gf will be injective. If f and g are surjective, then gf will be surjective. If f is injective and g is surjective, then gf taking x to z may or may not be injective or surjective. So before I go on, let's examine this in detail by kind of drawing a picture in paint to see why the composition may or may not be injective or surjective. Okay, so here I have a function f and I have a function g, so let's draw them out. So now what do I know about f or g? Well, f is injective, so that means it's going to be 1 to 1. So I could do something like map these 3 points here. Okay, now G is going to be surjective, so it needs to cover all of these elements, but it doesn't have to be injective, so it can map more than one element here to a single element here. So G could do something like this. So now, if I look at the composition GF, what would it do? Well, let's draw it in red. GF would take this element here, it would map it to this point, and then it would map it over to here. It would take this element here, it'd map it to here, and then map it all the way over to here. And it would take this element, map it here, and then map it over to here. So is this function injective? No. Why? Well, if I look over here, this element has two red lines pointing to it that corresponds to two different elements in X. So this violates injectivity. Is this surjective? No, because there's nothing in F that mapped to this element in G, so this element here doesn't have anything that maps to it. So this is the basic idea for why this bullet point holds. It's not a formal proof, but from this picture you can build a formal proof pretty easily. Okay, let's continue on. If F is surjective and G is injective, then again, GF from X to Z may or may not be injective or surjective. So now let's briefly look at why this one might be true. So I've pre-drawn a picture just to make it a little bit quicker so you don't have to see me draw it. So here, since F is a surjection, it has to map all of the elements in its domain to everything in this middle set, but it doesn't have to be injective, so I can map two things to one element here. Now, since G is injective, so it has to look like this, but it's not necessarily surjective, so there could be elements in this codomain here that don't get mapped to. So now from here, if I build the composition GF, it would take this element, go through this point, map it here. It would take this element, go through this point, map it here. And it would take this element, go through this point, and map it here. So clearly, this point here is a problem, since there's two things that get mapped to it. And this point here is a problem, since nothing maps to it. Thus, it may or may not be injective or surjective. Okay, so now if F and G are both bijective, then GF is bijective. So once we've proved these first 2 points, this third point comes directly from the fact that bijective functions are both injective and surjective. Next, if GF is injective, then F is injective. So if I know that the composition is injective, then I know the first function that gets applied has to be injective. And finally, if GF is surjective, then the last function I apply has to be surjective. So now, I drew pictures for these 2 points here, but there's pictures for the rest of these problems as well. And good practice would be to draw those pictures and see if you can convince yourself why this would be true before doing a formal proof. And if you have questions, I can go over any of that during office hours. Okay, so let's now prove the first one of these statements. So I'll prove if F and G are injective, then GF is injective. Okay, so to prove that if F and G are injective, then GF is injective, I'm first going to draw a diagram to see why it might be true. Again, these diagrams do not prove that something is true. It just gives me intuition of whether or not it would be true. And for functions, it can give me some idea of what I need to do in my formal proof to prove it. So here I have two sets X and Y. F is going to map from X to Y, and it's going to be injective. So what will F look like? Well, it could take this X, map it to some point here, this point, map it to that point over here, but the key idea is it's not taking 2 points and mapping it to a single point. Further, G is injective, so I'm going to have another set over here, Z, and since G is injective, it's going to map these 3 points to unique elements over here. So it could look something like this. So now if I consider the composition G of F, well, it's going to take this first point, it's going to go through here and map it over to here. It's going to take this point, it's going to go through here and map it over to here. Now, since F mapped unique elements to unique elements, and since G maps unique elements to unique elements, this composition must also map unique elements to unique elements. So again, this is not a formal proof, but it does suggest that the statement might be true, and it does give some hints on how to prove it. So explicitly, I'm going to start with some X's in X, note that they map it to unique things over here, and then I'm going to note that G takes those things and maps it to unique things over here, and then I'll be done. So let's give a formal proof for this. So now let F from X to Y and G from Y to Z be injective functions. So the first thing I need to do is I need to show that this GF is well defined. So now how do I do that? Well, I simply note that the range of f is a subset of the domain of G. In particular, the range of f is a subset of y, and the domain of G is y. Thus, GF does in fact exist. So next, what do I need to prove? Well, I need to show it's injective. So how do I do that? Well, my intuition from the picture that I previously drawn suggests that I first need to consider 2 points x1 and x2 in X, such that x1 is not equal to x2. So from here, what do I do? Well, let's note that since f is injective, f of x1 is not equal to f of x2. Unique elements of x get mapped to unique elements of y by f. Further, since f of x1 and f of x2 are now unique elements of y, I can use the injectiveness of G. So since G is injective, I know that G of f of x1 is not going to be equal to G of f of x2. And again, that simply comes from the fact that f of x1 does not equal f of x2. But this statement here is the statement that GF is injective, so hence GF is injective. So this is the type of proof I might want you to write on like a midterm, final, or in your homework. Now, let's prove that if GF is injective, then F is injective. Well, the best way to prove this is to do proof by contradiction. So kinda why? Well, for a direct proof, I'm dealing with this GF itself, and I can't really separate out F given a function GF. F could be lots of things. So I can't really directly show that F has to be injective. So using contradiction or the contrapositive is kind of the way to go here. So proof by contradiction. Let F be a mapping from X to Y, let G be a mapping from Y to Z, and let GF be a mapping from X to Z be functions such that GF is injective. So here, note that I'm explicitly letting GF be a function. I'm not proving that GF is a function, and that's purely because here my statement is if GF is an injection. So I'm starting with the composition itself. Okay, so now that we know why we can start with GF as a function, what do we need to do from here? Well, I said I'm going to do proof by contradiction, so my next sentence better tell me that I'm doing proof by contradiction. So assume for the sake of contradiction that F is not injective. Okay, so F isn't injective, now how does that help me? Well, since F's not injective, that tells me that there exist x1 and x2 such that f of x1 is equal to f of x2. And what do I know about these two elements, x1 and x2? Well, x1 is not equal to x2, just by the definition of not being injective. So now what can I do? Well, I know GF will have to take these elements f of x1 and f of x2 and map it to something. So explicitly, since f of x1 and f of x2 are elements of y, they are mapped by G to some z1 and z2 in Z. But very importantly, f of x1 is equal to f of x2, so they're going to be mapped to the same element of Z. Thus, G of f of x1 is equal to G of f of x2. But this was a contradiction that GF was injective because it takes two different elements in the set X and maps it to the same thing in Z. Thus, since this is a contradiction, we must have that f is injective. So now let's define the identity function. So a function I from x to x defined by I takes x and maps it to x is called the identity function. So this is similar to, say, the identity matrix in linear algebra. So now we can give a theorem. If f mapping from x to y is bijective, then f of f inverse, which will map from y into y, and f inverse of f, which will map from x into x, are the identity functions on y and x respectively. So this is kind of the classic thing that you want your inverses to do. This is explicitly saying that your inverses of a bijective function undo what the function does. Now we might ask, is bijectivity here required? Could I just have injectivity and have this work? Well, being injective is not enough for this theorem, as stated, since the domain of f inverse needs to be equal to the codomain of f for this function here to be a mapping from y to y. So you could modify this theorem to be valid for injective functions by changing this y here and this y here to simply be the range of f. And then it would be true for injections. So now let's give a formal proof of this. Let f from x to y be bijective. It follows that the range of f is y, since f is bijective, thus f inverse from y to x exists. So this is the step in my proof where I'm using the surjectivity of f. Okay, so now that we know this inverse exists, what next? Well, I need to I need to note that these compositions are now well defined. Well, hence, f of f inverse will now map from y to y. Why would this be true? Well, f inverse maps from y to x, and x maps from x to y, pretty trivial. And f inverse of f will map from x to x. Why is this true? Well, f maps from x to y, and f inverse maps from y to x. So that would be true. So now that these function compositions are defined on the domain and codomain that I wanted them to be defined on, I need to show that they are in fact the identity functions between those two sets. So how do I do this? Well, it's pretty straightforward. So if I pick any y and y and any x and x, then the following holds. F of f inverse of y, what will that be equal to? Well, that will be the same thing as f of f inverse of y, and simply because f and f inverse undo each other, that'll simply be equal to y. Further, I get the same type of thing happening for f inverse of f of x. I get that expansion and then simply x. Okay, so we have one more thing to talk about in this lecture. If f is a function from x to y, and g is a function from y to z that are both bijective, then gf exists and is invertible. So the main thing to get out of this point is that the composition is invertible in this case. F inverse of G inverse exists, and the inverse of the composition GF is the same thing as F inverse times G inverse. So you may have seen this rule previously for matrices, and the idea here is similar. So let's end this lecture with a proof. So let F from X to Y and G from Y to Z be bijective functions. So to prove this first point, I need to show that GF exists, and then I need to show that it's invertible. So to show that GF exists, what do? Well, I simply note that the range of F is equal to Y, and that's simply going to be a subset of the domain of G. So here explicitly, I have the range is equal to Y because F is bijective. So since this is true, I now know that this composition exists. So now I need to show that this composition is invertible. Well, how can I do that? So I can note that since f and g are bijective, my previous claim said that the composition of bijective functions is bijective, therefore gf will be bijective, and since gf is bijective, it's injective and thus invertible. So now I have proven this first part here. So next I need to show that f inverse g inverse exists. So to do this, I'll first start by showing that f inverse and g inverse on their own exist, and then I'll show that the composition exists. So since f and g are bijective, f inverse from y to x and g inverse from z to y both exist. So here I'm using the surjectiveness of f and g to make this a y and a z instead of the range of f and the range of g respectively. Okay, so now I need to show that this composition f inverse of g inverse exists. Well, that's pretty trivial. The codomain of g inverse is y and the domain of f inverse is y. Thus, the composition f inverse g inverse also exists since what I just said in words. So that's done with the second part. Now for the third part, how do I show that that is true? Well, I already know that gf exists and is invertible, but I do need to know what its domain and codomain are. So explicitly from the third part, notice that since gf is bijective, this inverse maps from z to x and it exists. We already had the existence from part 1, but we do need this domain and codomain here. So now we need to show three things. We need to show that the domain and codomain of these two functions are the same, and we need to show that they act on any element of z in the same way. So showing that the domain and codomain are the same is pretty trivial. The domain of both of them are just z, so I'm done. Similarly, the codomain of both of the functions are both x, so I'm done there. So finally, we need to show that this function here is in fact the inverse of gf. So how can I do this? Well, I can simply show that the two functions undo each other. So formally, for all x and x, I can use the associativity of this to rewrite this as f inverse of g of f. G inverse of g, well, that's simply going to be the identity function on y. So here I'm using this new notation I sub y to tell me that this is the function from y to y that maps any element of little y to the same element little y. So now this triple composition here simplifies to this just by the definition of the identity function. And now f inverse of f, well, that's simply just going to be x. And finally, I also need to show that they undo themselves in the other order. So explicitly, I need to show that this holds for all y and y. Why do I need to do this? Well, recall that functions are not commutative Therefore, for the functions to be inverses of each other, they need to cancel out in both directions. So here I want you to think, say, left inverses and right inverses of matrices. Okay, so that's that for this proof. And we have no assigned reading today, but we do have this meme.